Hi everyone, thank you so much for that. So today I'm going to talk to you a little bit about this latent factor regression work, but I wanted to start by just kind of giving you a little bit of background on my research agenda, since this is sort of the first time I've taught in this seminar, and there may be some people that don't know what I do. Very broadly speaking, my goal is to democratize statistics. There is a tension, I think, between the need to acquire technical skills in order to do fancy statistical things and the knowledge of substantive problems that actually makes research work very well. And it's settings where you have that combination of the two. You have the neat statistical methods, but you also really have a deep understanding of your problem that the learning really gets done. And so I want to do what I can to sort of make the statistical methods as easy to access for people as possible. And so the way that I think about doing that is working with practitioners who have a specific methods problem, and then I try to solve that problem and, importantly, generalize the solution so it solves other people's problems. And so I'll be really curious to sort of talk to people in the Q&A and afterwards about where you think this kind of technology could be useful for your own work or more broadly in demography. The second thing, and this is part of generalizing for other settings, is I like to build custom problem-specific models in a very general framework. So what I want you to be able to do is bring as much background knowledge as you have about your particular problem to bear, but without needing you to sort of program up and derive a new model, which I think is sort of realistically just beyond what most people are going to want to do. So a lot of my prior work, as was mentioned in the very nice introduction, has been in statistical text analysis, and particularly developed a model called the structural topic model that follows in this same frame. It's sort of a way of designing a text analysis model that builds in the context of who documents were written by, when they were written, all these sorts of things you can sort of build into your own model. So again, I want to get feedback from you guys about applications of this stuff in demography. So let's jump in by sort of motivating the study of heterogeneity. We have lots of data that comes from lots of different sources and has lots of different structure built into it. So one of the things about the big data revolution is that it's not just really big data, it's really big collections of lots of little data sets. And so it might be that you have a bunch of data for a different set of countries, that you have some trends over time, and so there's this sort of temporal structure, that there's locations that are situated in a space or nodes in a network. And where things get really complicated is when you have to actually deal with like all of these things at the same time, and that's when most existing methods sort of start to fall apart. So along with these different types of data, there's different heterogeneous effects of interest. So we might care about, for example, how the effect of some program varies by country. We might care about time-sensitive effects, right? Is it more effective at the beginning than it is later on? We might care about diffusion over space. So if a country becomes democratic, does its neighboring country become democratic? We might care about contagion in a network, which is basically the same thing, just in a network instead of over space. And again, combinations of the above, which I think have sort of largely been out of reach, and I'm trying to bring them more into a realm where we could work with those types of models. So this is a marked difference in some ways from the way qualitative scholars deal with these problems, where they're often very focused on recognizing the unique features of individual cases, which gives that work a certain type of analytical leverage. Quantitative studies often end up ignoring heterogeneity and focusing on average effects, or sort of treating all units as the same. And this is weakened somewhat by the inclusion of covariates into models, right? Which is essentially a way of using an observed variable to look at differences amongst units. But it's limited to the covariates that we happen to have available to us, that have been, kindly collected by some government or some other scholar, or we've collected ourselves. And what this often does is it discards a lot of information that we actually know. We know that these things happened over time, but maybe we don't know exactly all the things that happened in all those time steps. Or we know that it happened across different countries, but we don't have all the background information we would like to have about those countries. It also ignores connections between units. So we might know, for example, that the friend of a friend is likely to be a friend. And those sorts of second order and third order connections are sometimes set aside in statistical analyses. So the problem with all of this is when you do this, you estimate your uncertainty incorrectly in the model, you get biased point estimates, and more importantly, you miss huge opportunities to say something interesting about the variety of experiences in the world. So strategies that we can use, well, we could go and we could collect better data, right? I said like one of the ways that you can sort of get around this problem is by knowing all of the things that say make a particular time period or a particular country different from other time periods and countries. But from a practical perspective, that's not always possible. And so we might characterize it as hard, but probably optimal. The second way is we can just kind of pretend the problem doesn't exist, like a classic strategy for dealing with methodological issues. And we might describe that as easy, but suboptimal, which the easy depends on your optimism, perhaps. And then finally, we can model unit heterogeneity, so we can explicitly have a model that sort of captures the differences amongst units. And that is, my goal here is to take this strategy and make it easy and near optimal, right? So it's not going to be the same as if you actually observed all the data about these units, but we're going to see like how far we can get and how easy we can and accessible we can make that for people. So the approach that I'm going to propose is using latent traits to model heterogeneity. And it's a framework that I'm going to call latent factor regression. So the idea is we're going to start by specifying the repeated units in the data. So we have a bunch of countries that are observed at a particular time unit. Maybe we have a bunch of observations for a given country or a given county. Perhaps there's like lots of different causes of death that we think are sort of all vaguely related to each other. There's some notion of repeated units here. And then what we're going to do is we're going to infer latent or unobserved traits for each of those units. So we get to see sort of repeated patterns. We get to see a particular country happening over time. And so we're going to borrow information from other countries to say something about each country individually. And then finally, we're going to estimate a regression that controls for those latent traits. So we're basically going to learn the thing we don't have and then have just kind of like a standard regression that will help us get at that information. And in practice, what we're going to do is we're going to do these last two steps, the inferring and the estimation, sort of jointly in one process. So it's going to help us describe how the units are related to each other. It's going to give us a parsimonious explanation of outcomes that we can use, for example, for theory testing. And it's going to give us sort of leverage to help predict future outcomes, because we're going to know more about the data. So we've learned something, say, from the past history of a country, and that's going to give us a particular type of leverage about predicting future outcomes for that country. The advantages here is that it's going to be a very flexible framework. It's going to be relatively simple, although, depending on your mathematical background, you can let me know if you find it simple, and we'll assess. And then it's going to be fast. So the plan I'm going to take here is I've given you a little bit of introduction. I'm going to talk about what latent traits are and why inferring them is helpful. I'm going to talk about estimation just a little bit. We're not going to go deep into the weeds on this. But I want to give you a sense of generality of the framework and how setting up one infrastructure can help us produce lots of little custom specific models. I'm going to give you an example using foreign direct investment and how international agreements affect that. I'm going to talk and reference a little bit an example that's in the paper about the democratic peace hypothesis, but I'm not going to talk about it just for time in the talk very much, and then we'll sort of wrap up, take some questions. So first, I want to give you a sense of the two problems that I consider in the paper, because I think it'll give you a sense of how the framework, what the framework works with, and like what is in common about these two different settings. So one question that's considered by Helen Milner and Tim Buta is, does joining an international agreement increase foreign direct investment? And they have, to solve this problem, some country year data. So you have a bunch of countries over time, and you have whether or not they're a part of say, the WTO or GATT, and you have their rates of foreign direct investment. And so their previous empirical strategy for dealing with the background heterogeneity here had been to use linear time detrending and country fixed effects. So you're basically dealing with time invariant characteristics of the countries, and you're dealing with some very strongly parameterized notion of a global time trend in the economy. Right? By strongly parameterized, I just mean it has to lie exactly along a line. Right? The second example is going to be are two democratic countries less likely to go to war with each other. And here you have a more complicated data structure, which I'm mostly referencing just to show that this doesn't have to be country year data. It is directed dyadic year data. So it's this country does this thing to a different country at this particular year, right? And so, and we could imagine that this could have lots of forms. It could be, for example, like different causes of death over time amongst different genders. Like there's all kinds of structure we could consider putting into the data. And I'm really curious about the kinds of structures that you guys encounter in demographic problems that might be useful to think about here. So the previous empirical strategies have been to use additive country fixed effects, which again are going to sort of deal with things that are time invariant about a country, but nothing, for example, about the way the country is embedded in the global security community, right? So it tells us nothing about the fact that, say, an enemy of the U.S., two enemies of the U.S. might be likely to sort of befriend each other just out of virtue of like strategic considerations. So we might think about this as capturing roughly how bellicose a country is towards every other country, but not sort of how bellicose they are to like particular countries. So, so the method I'm going to present here is sufficiently general to cover both of these cases and a lot more. So in both settings, basically what's happening is that we need to control for information that we fundamentally don't have. We know who the countries are, we don't know all the underlying properties of these countries. And so what we're going to do is we're going to specify repeated units in the data, so the countries and the years. And that's going to tell us something about which units we expect to be heterogeneous in some way. So, so in the FDI case, we have countries and years. In the democratic peace case, we have the source country, the target country, and the year. So units have, under this framework, common unmeasured components that create dependence between the observations. And the fundamental premise is if we knew this set of things, then we could rightfully treat all of these observations as independent. So, so we're going to infer what those things are for each unit. So we'll specify a model, like a data generating process for those latent traits, and we're going to allow the traits to interact across units to produce more complicated effects. So rather than being stuck with, say, just a country effect that has to be time invariant, we're going to sort of allow the country effect to vary over time. And so the trick here is that we have repeated patterns of data, and we're going to make some assumptions about essentially the simplicity of these patterns in order to get some leverage in learning them. And then finally, as I said, this is sort of part of the process, we'll estimate a regression that controls for these latent traits, and then you'll get a regression just sort of like you normally get. Okay. So before going too much farther, I want to say, like, do we need this framework? Aren't there other ways of solving this problem? And yeah, there's a few. So you know, there's fixed effects, which is like the econometric standby. There's random effects. There's multi-level models. But it turns out there's like many other approaches. And this turns out to be a problem. Like I literally just sort of stopped when the slide was full. But there's lots of other things that you could add here. And there's different methods essentially for every type of problem. And we go back to the thing that I was sort of talking about on the introductory slide, which is that when you have combinations of these things, when you have, say, spatial and temporal dependence, a lot of these things fall apart because they're designed to deal with just one of those things. And so a lot of these, I'd say most of them fit into the estimation framework that I have. And the estimation framework can sort of deal with the problems that are posed by all of these things, even if they're not special cases. So here's the thing. I've been sort of talking this up for the last 15 minutes, but like, here we go. This is what it is, okay? So, so there's going to be some outcome. It's going to come from a distribution from an exponential family. If you don't know what that is, that's okay. It's pretty much every statistical distribution you've heard of, okay? So there's going to be some link function, kind of like you would have in, say, a logistic regression. And there's going to be some linear predictor, just like you would have in any regression. So, so the key thing here is that the observed outcome, right up here, is a function of some observed covariates, and then there's just a whole bunch of other things that we're going to estimate. The key thing that we also have here is that we're going to have some unobserved traits that are going to hang out in this linear predictor as well. And I'm going to break this down for you in a simpler case that has a sort of less imposing form. Okay? On top of all of this, we're going to give these all things a prior because we're going to be Bayesian about this. And what you can think about that doing, if you haven't worked in the Bayesian framework, is providing an opportunity for the analyst to give information. And in this case, the information that the analyst is giving is where we expect smoothness. So we might, for example, expect that the country in 1990 is very similar to the country in 1991. And that's something that we can bake in without sort of forcing it to be true, but sort of expressing a preference for that to be the case. And Gaussian Markov random field is a very, very general way of doing that. Okay. So here's a special case for the setting of foreign direct investment, and I'm just going to walk you through it so that we have kind of a concrete sense in our head of what it is that's being proposed here. So this is the full model. It's very scary. I'm going to get rid of all this stuff down here, and we're just going to talk about the part up here. Okay? And there's a few different pieces going on. So if we just had this outcome, this regression term, and this unstructured error, it would look exactly like linear regression, right? And we would be comfortable with it. So these additive traits right here, you can think of as like two-way fixed effects, more or less, right? So. So this is unit-specific additive traits. So one example is like country year intercepts that you might add, right? Just sort of allows everything to be a mean shift away. In a network case, you might think about it as node popularity. And in a general statistical sense, it's sort of falling under that framework that's set up by fixed and random effects. Okay, but the key thing that is common to all of these is that the effect that we're estimating for, say, a country is common to that entire unit. So it is a property about the country, for example, that does not change, or a property about the year that is true across all countries. So what is going to be different about this setup is this piece over here, which are the interactive traits. And these are things that are going to be able to be context specific. So we can think about economic shocks with varying responses. So something like, say, the Asian financial crisis hits certain countries in a common way, but doesn't affect other countries, right? Or say a commodity spikes, right? That will affect exporters and importers of that commodity, but probably not places that don't have meaningful exchanges of it otherwise. We could also think about it as communities in a network. So a form like this can capture the kind of friend of a friend is a friend type logic. We can also think about it as a regression of country attributes with time-specific coefficients. So if we knew the property of the unit, then we could think about all we're doing is sort of allowing the way that property affects the unit to vary, by year. And then finally, the last piece here is just, there's going to be k of these things. There's a little summation here, and that's going to indicate the number of traits, which, as you'll see in a second, allows us to control model complexity. So as we allow for more traits, we're sort of allowing the trends that we learned for each country to sort of separate from each other. And you can imagine the special case where k is 0, it just sort of collapses back on like a fixed random effects type structure. Is everyone with me so far? Awesome. Okay, so I'm just going to give you a nice little visual example so you can see how this plays out. So we're going to say that we're going to just start with these particular time factors. So here is one. It is a trend of like essentially globally a particular archetypal pattern of what's going on with foreign direct investment. And here's a second factor. And I'm going to give you an example that just has two factors, which is much simpler than the actual fit to the data, but is going to make the pictures work a lot better. Okay, so let's start with Malaysia. The contribution from the factors is up here, right? And I just showed you what these V's look like over time. That's these two things. And so let's just start by throwing one of those V's, that first one, up on the board. So this is a particular time trend, and we want to see how is Malaysia sensitive to this particular time trend. And so we estimate some number, which in this case turns out to be negative 0.73. And so essentially that solid line just kind of flips up, and we get this, this dotted line. Okay. So now we have how Malaysia has expressed along this first factor. Okay. So we can do the same thing with the second one. The sort of translation is very similar, and so you get something that looks a lot like the sort of archetypical version of the second factor. You put them together and you add them, right? And you get this blue line, which is just the addition of these gray lines to each other. Yes, please.
So where did you get those two factors from?
So these are all learned from the data. So I'm sort of, I'm basically stating, I'm providing you the V's here, but they were also estimated. And so the idea is that we're going to sort of constrain the data in this context to, absent all the observed covariates, everything else that's going on has to be explained by some linear combination of these two, or like linear translation of these two factors, plus some like random noise.
And you specify the number of factors in advance.
No, we're going to learn it, which is great. You could also specify it if you wanted to, but the theory I'm operating under is very, very rarely do we have any sort of a priori notion of what it is, because if we knew what it was, we could just go like collect the data on it.
So before you did this, you ran a factor analysis and then you fed it into the model?
No, so this is actually going to be, it's sort of like a factor, like the reason, the nature of the name is that basically you're doing like a factor analysis inside the regression. So if we did the factor analysis first, the problem that we would have is that it would also capture all the stuff that we observe. But we want this to just capture like the unobserved stuff.
Just to prevent other people from asking more questions, this is very, very analogous to big N, small n in fertility. I worked on similar things. I'll send you. It's very similar. Think of lambda for age effect, then big N, small n. This is kind of small n for country-specific regime fertility controls.
Interesting. Cool. Well, I'm looking forward to reading about this. See, this is why I'm here. I'm very excited. Okay. And I should say, actually, to that point, one of the things I'll talk about in a second is this central core idea has been reinvented across a lot of different fields. And as best I can tell, none of these fields actually talk to each other or cite each other. And so one of the advantages of the paper is that there's quite an extensive lit review in it of what's going on, although clearly I missed some things in demography, so this is very exciting. But I mean, there's like 15 pages of citations just because there's this many places have sort of picked up this core idea. Okay, so, right, so we did this little example. So now I'm going to kind of show you how this fits the data. So here's sort of the predicted values. The shape has changed a little bit because we've incorporated the observed information that we had about Malaysia. And so here's the truth. And you can see the truth is a little bit more erratic than the trend we predicted, but that's, you know, sort of consistent with like all predictions look like with observed data, right? There's some element of noise there. And here's what you get out of the linear model that Milner and Buter are running, right? And so what you can see is that we've really missed like the whole Asian financial crisis, that the whole construction of the global linear trend means that it has to keep going up here, right? That's the nature of a line, but we're able to sort of capture this like peak and drop off, albeit slightly late. Now, one of the natural concerns that you have to ask about with a flexible model is what we're seeing just overfitting, right? And so this was actually all run with data held out. And so the data, and I can't tell if you can see it from there, there's sort of like these like pink streaks. I don't know if you guys can see that. Okay, good. So those are all held out data, right? And so the model did not have access to those when learning the predictions. And so you can see that those do not look atypical in terms of like it is not as though it fits perfectly along areas where it had data and then it's just like crazy erratic where it doesn't, which is, you know, the thing we want to see. So here's another example for Indonesia. You can see it has a very similar trend, also sort of dealing with the Asian financial crisis. And here's the example of the truth, the linear trend, and the held out information, right? And actually, I was very pleased that I was even able to get this kind of level of drop off here, given that the 2 data points at the beginning of the drop off ended up held out. Right, but it's still able to figure out that there's some drop happening, it's just not getting quite the severity of it.
You're holding out different data for each case here?
Yeah. So I'm basically, if there's a matrix of like countries by time, I'm just randomly selecting entries to pull out. Now, what other option would be to take like, say, a whole year? That ends up leaning a lot more heavily on the prior infrastructure because you have to find some way to learn the information about that year. And you don't have it like, so it's much easier when, for example, you're comfortable making an assumption of smoothness, because then you can sort of learn from the years around it. Okay. Here's just another example from the Philippines, just to kind of, again, give you some sense. And again, all of these things with the linear trends all end up exhibiting this same sort of infrastructure, which is why like we might be worried about it.
And you randomly withhold data.
And we're randomly withholding data.
And
No, not just for demonstration
just
purposes.
for demonstration.
Yeah, we don't let in your real case you use all the data you have because you know why not? Wait, you know I'm just tying my hands behind my back for this presentation, guys. It's fun. Okay, so one thing I want to show is that it's not just the Asian financial crisis. Here's some examples, and all I've done here is plotted the points for some areas in the Latin American debt crisis and sort of showed you what the trends look like, right? And so it's not just that the model has underlying learned like the Asian financial crisis and that's all it can reproduce. It's that even with only 2 factors, it is able to consider like a variety of trends. Also, sort of showing you these 2 at the same time is another way of emphasizing what's really going on here. It's not that the trend has to look exactly the same for each country, it's that they have some structural similarity. And so you can see there's like a shape that's being learned here, and this goes to why the model is actually able to do this, right? It's not magic, it's that lots of countries experience this crisis in approximately the same way. And if that hadn't been true, it was specific to one country, then the model's gonna miss it. Right, because it needs that repetition in order to pick something up. But you know, you can take heart in the fact that like anything is going to miss it if it's just one country, right? That's just the nature of like you only have one unit at that point. So this framework is pretty flexible. So if you have just a single type of unit, right, instead of countries and years, you just had countries. This sort of falls back on like standard hierarchical and multi-level modeling. So you think like Gelman and Hill's textbook or something like that. This is what this all collapses back to. The number of traits here is going to control model complexity. And so it's going to generalize the 2-way effects framework or multi-way effects framework more generally when k equals 0. So when you drop out these interactive components, you just end up back with that setting. When k is exactly the same as the number of units you have, you get completely unique effects and the model is like hopelessly unidentified, right? And so every k between 0 and the number of units is providing sort of a step closer towards like a completely unique fit for every unit. And so we're going to estimate this k in order to find what is essentially a data-driven trade-off for this problem. More traits basically means that units can be similar to each other in different ways. So a natural way to think about this might be the notion of a network, right? So if you wanted to predict the ties between people, you might think about using communities to do that. And the number of traits is roughly like the number of communities. It's a very rough approximation, but I'm sort of giving you a sense of like, there are different ways people could be associated together. So what's nice about this is mathematically this extends really easily to higher dimensions, right? So I'm giving an example of countries and years, but it could be that you have a country, a year, a wave of a survey, a subnational unit, male and female, racial groups. Like you could do all kinds of cuts along the data, whatever sort of structure is particularly relevant or interesting for your problem. And again, the traits can be estimated because we have repetition of those units. So this core approach has appeared across many fields, including apparently demography, which is cool. Okay, so now I'm just going to talk very briefly about how we go about estimating this. The thing we need here is a fast estimation framework, and so we're going to do Bayesian inference through something called variational inference. So in the 1980s and the 1990s, the approach to doing Bayesian inference was Markov chain Monte Carlo. It is asymptotically accurate and it is sampling based. So it basically means if you are willing to run the chain for infinity time, you will correctly recover the posterior. Okay? So in the late 1990s and 2000s, coming out of the work in statistical physics and picked up heavily in computer science, you get variational inference. And variational inference is a very fast, approximate, deterministic estimation strategy. So it means that, like, asymptotically, you will not perfectly recover the posterior, but what we'll see is that we can actually produce a relatively tight approximation, but in like fractions and fractions and fractions of the time. And so we take estimation that quite literally took weeks to do some of these models, and you bring it down to the scale of seconds. And this is, on the one hand, it's important, like, so like a thing methodologists do, like to boast, is they're like, oh, my software is so fast, like, look how much time I've shaved off. But it's beyond boasting. It's important because weeks, in some sense, is like actually forever, right? Because it changes fundamentally the way that you interact with the model. You're not going to do model building and checking. You're not going to like consider an alternate specification for those reviewers. You're not going to do any of this if it takes weeks to estimate, because you're going to run it once and then you're going to be done, right? Because it took weeks. And so this is you know, maybe like it's much easier for you to just kind of pick up and try this on your problem. Whereas like even if the software is easy to use, you're not going to just pick up and try something that takes you weeks to estimate. Or maybe you guys would because you have more patience than me, but I wouldn't. So the basic procedure, just to give you a flavor for how this works, is that we estimate the unobserved traits for each country. We then estimate the unobserved traits for each time period. We then estimate the regression coefficients of the observed covariates, and we just keep repeating. So then based on this other thing, we go back up to the top and we just cycle. And this is a process called variational expectation maximization. If you're in my class now, we will learn about this in like week 9, I think. So exciting times, guys. But this is, you know, good stuff. So each step of this iterative procedure is just a regression, which is how we're sort of able to make it fast, because over the years we've gotten very good at making regression very quick. Okay. I'm working seemingly for a very long time, but I've been working on easy-to-use R software that will do all this for you. And I'd actually be very interested in talking to people about sort of what they want from their hierarchical modeling software, like what features, you know, and things they've used before have like not made them very happy, because I would like to be able to do better in the interface for this. Okay, so I'm going to do one slide that's like slightly more technical for the statsy people in the room, and it's okay. Like if this one slide doesn't make you happy, it's all right. Like I'll get back to simpler things in a second. So there's some complications here that go beyond standard variational inference. The first is that a lot of these problems are sort of badly non-conjugate. So generalized linear models often have non-conjugacies. You think, for example, logistic regression is going to be non-conjugate. The variance components we're going to use, instead of using sort of classically conjugate variance components that have some problems, we're going to use some better things like half Cauchy distributions and scaled inverse Wisharts that are going to be more weakly informative than the conjugate options. We also need to be very careful in initializing this model. So the posterior distribution is multimodal, right? The surface is bumpy, and you're only guaranteed to find a local maximum. And so you need to find some way of making sure that you start in the right place so that that local maximum is as good as humanly possible. And this is a thing I've worked on a bunch in topic models, but it turns out like we can do a similar sort of structure here. There are ways to make sure that matrix decompositions have global guarantees. And so for 2 units, we can do that. For 3+ units, we can use tensor decompositions, which have essentially probabilistic guarantees. So we can't be sure for this sample we found the global maximum, but we know like across samples in general with high probability we will find the maximum. We're also going to do automatic methods for rank selection, so we're going to pick the complexity of the model based on the complexity of the data. This is a process called automatic relevance determination, and another alternative I discussed in the paper is something called the multiplicative gamma process prior. Okay. So this is all stuff that is very hard behind the scenes, but the key is making it not hard for the user. And that's the sort of notion of the software. So the reason all of this works is because we're very carefully leveraging information we have. We don't know the unit traits, and if we could measure the covariates, we would include them. But we do know what the units are, right? That's something that people are very good at specifying. When you have a firm understanding of your problem, you often know where the holes are in your data collection. And so you can talk very eloquently and precisely about like what is the piece that we wish we had. And so theory is going to help us with this. Qualitative scholars are often also very helpful for this. And so we can think about it as the same information that we're putting in when we do fixed effects or something like clustered standard errors. We're just using that same information more efficiently and flexibly. Okay, so I'm going to very quickly give you an actual applied example of this with foreign direct investment. This comes from some work by Tim Buta and Helen Milner, Helen who is here in the politics department. And they were studying the determinants of FDI, foreign direct investment. Okay. So just moving quickly so we have time for Q&A, I'll just say again, their approach to this is to deal with temporal issues by linear time detrending and country fixed effects. So this ends up getting critiqued in this paper by Gary King and Molly Roberts that is really about the problems with robust standard errors. And so they choose this article and this particular model, and they basically say, look, there is some country-specific time dependence that's happening here that is causing huge problems that the robust standard errors are like not addressing. And so they go in and they re-specify by giving every country a quadratic time trend. So 2 things have changed here, right? They've gone from a line to a parabola, right? And they've made it country-specific. And that's going to be the big thing. Every country is going to get its own trend. The WTO effect goes to 0 under this new version, and they sort of say, well, maybe there isn't evidence for what's going on. So here's the figure from their paper. There's some models over here. This is the nice effect that Helen likes, and this is what they published in their paper, which is, not great because the confidence interval overlaps 0, and obviously that makes it hard to publish things. So let's talk about what's going on here, because there could be a couple of things going on. It could be that what has happened is simply that we've used too aggressive a model, right? So we've captured some of this dependence, but we've washed out everything that is related to the effect of interest. And so we're going to go in and we're going to specify a model that has these interactive effects. So the key thing here is that unlike the previous 2 works, not only are we going to get country-specific time effects, we're going to make no functional form assumption for time, right? You saw those like jagged pictures I had for like Malaysia and Indonesia and such, right? We're not assuming these things have to follow along a line or like a smooth curve. And when you do this, you get some nice effects that are, I would say, slightly smaller than the ones that Helen reports in the paper, but are nonetheless significant and positive, which is like certainly what we would expect given the literature, even just beyond this one paper. So I wanted to give you a sense of like how this differs, and so here's a plot of some data. These are residuals along with the quadratic trend, which is in red, the latent factors model, which is in green, so it's tracing there, and the linear detrending, which looks like this. And what I want you to take away from this is that when we look at the residuals, the model fits are like roughly the same for the quadratic and the latent factor regression. So it's not just that it's fitting the data so much worse that, that like somehow this effect is coming back. It's fitting the data equally well. I would argue actually even better in certain places. Here's another example, and you can see what King and Roberts are reacting to, though, right? This black line is like, that is a huge trend in the residuals, right? That is not something that you really want to see. Here's another example where things go particularly awry, and again, we have this nice sort of flat line that goes through the residuals for latent factors and for the quadratic models. So what's going on here? Well, when you do linear global detrending with country fixed effects, what you're basically fitting is a bunch of lines that are shifted from each other. And so I've just sort of plotted for you what's going on with the unobserved piece of the model here, right? So by contrast, here's what King and Roberts are doing, right? They're just fitting little parabolas for everything. And you can see the parabola shapes and scales get really big and random because there's just not a lot of data there, and so it's very difficult to kind of keep those things from going all over the place. So by contrast, here's two-way fixed effects to give you a sense. It's going to be a fancy shape, but everything's going to be mean shifted away. And here's what the latent factor regression gives you, right? And so there's some substantial structure here, but for the most part, everything is sort of getting its own sort of slightly constrained time trend. Okay. So just to wrap up, I'll say that the data and the quantities that we're interested in are often heterogeneous. I've focused here on sort of heterogeneity that is in the background, but we also can use this exact same method to apply for like heterogeneity of how an observed covariate affects the outcome. So something like, does the implementation of a particular social program vary by region of the country, right? Like you could capture that kind of thing as well. It's going to allow us to use lots of types of data, group data, network data, time series, cross-sectional, et cetera, et cetera. And it's going to let us get at all these kinds of quantities of interest that are sort of driven by heterogeneity. So, and I'll note, even if you're sort of not implicitly interested in heterogeneity, it's important just to get average effects correctly to like model this stuff in the background well. So it's a way to do this. It's very flexible. It's relatively simple in that it's an extension of the standard regression framework that we all know and love and mildly hate. And it's fast, right? It's going to let us do this thing on the scale of seconds, maybe minutes on the high end, rather than minutes to days to weeks, right? The paper has a lot of additional material I'm not covering today, a lot more on the priors that allow you to say, specify things like smoothness over space, so like neighbors should behave similarly, or smoothness over time, that sort of thing. And then a bunch of details on estimation, because obviously there are like pages and pages and pages of math that go with all of this. As well as the extensive literature review I mentioned earlier that is apparently not extensive enough in demography, but it will be, guys. It's going to be great. So future work, the biggest thing I need to do is produce software. There's some computational improvements. There's some ways to make these things even tighter to the true posterior, which I would like to do. I would like to build in a set of diagnostics, and I think it would be helpful to know like kind of what diagnostics people typically find helpful, like or what they want to do in unpacking their model, because I want to make that as easy as possible. That's been a big part of my text analysis work, is taking the things we all ought to be doing all the time and making them easy to do in the software so people actually do them, right? And then applications, which again, I'm very interested in talking to people. So anyway, thank you so much for your time, and I'm happy to take questions.